Chapter 34, Electromagnetic Waves. This is the last chapter of Electricity and Magnetism in Physics 1C. Starting from the next chapter, we're gonna get into optics. Okay, so since this is the last chapter, let's see. Let's take a look at what we have studied so far for E and M. Let's put all the existing laws that we've studied about E and M together. And we ask ourselves, how many laws have we studied so far? Are there anything new to be discovered, or there are just the right number of laws? Well, let's see here. We have studied Gauss's law for electricity, otherwise known as Coulomb's law, right? That is one of them. And then we have another one, which is the Gauss's law for magnetism, right? That's another one. And what else? Well, there's Ampere's law that tells you how to generate a magnetic field with an electrical current. And what else? And there is Faraday's law of induction, right? So we have so far studied 4 laws, okay? And why 4? Why is that 3 is not enough? And could there be a 5th or more laws describing the electromagnetic fields? Well, it turns out this question can be answered from a mathematical point of view. Okay, after all, what we need to describe are 2 vector fields, E and B. My question is this: how many equations does it take to uniquely specify a vector field, such as vector E and vector B? Okay. Well, to answer this question, we have to review a little bit of vector analysis in mathematics. It turns out that any vector field in general can always be decomposed into 2 types. One is called the longitudinal, and the other is called transverse component. Okay, a longitudinal vector field. If I draw a visual picture, you would get something like this. Okay, such as, you have a positive charge, you got field lines streaming out from the positive charge, or if you got a negative charge, you got field lines getting merging into it. So a longitudinal field have field lines emerging from something or disappearing into something. In other words, they have a source where field lines come out, or they have a sink where field lines go in. This is what's called a longitudinal field. Okay. On the other hand, a transverse field is like a whirlpool. It has no beginning, no end. Okay. The field lines which simply start from nowhere, end up nowhere, just keep on going, keep on going, keep on going. There is no source and there is no sink. Okay. These are 2 general types of vector fields. And if you just look at an arbitrary vector field, it may consist of both types of components. It may have both longitudinal and transverse components. Okay, now how does one describe the longitudinal part and the transverse part? Well, it turns out the longitudinal part of a vector field can be described by the divergence operator, gradient dot. And the transverse part can be described with a rotation operator, gradient cross. This is something we learn in a vector analysis class. Okay, but going to our case, how does one apply this knowledge to the electromagnetic fields? Well, one thing we can do is we already have the 4 laws that we've studied, but these are all in integral forms, right? What we want to do now is to convert them into differential forms so that we can see the divergence and rotation used to express the vector fields of E and B. Okay, let's see how we can do that. As an example, let's convert the Gauss's law into differential form. Okay, Gauss's law for electricity and Gauss's law for magnetism. To do so, we need a theorem in vector analysis, and it's called the divergence theorem. What's the divergence theorem tell us? Well, it says that if you have an arbitrary enclosed region in space, the volume is V, and the border region, okay, the border surface is A, and then there is a vector field psi, okay, that streams in or out of the area which contains the volume V. Then it turns out that the surface integral of psi dot dA over the surface A, which contains the volume V, can be converted into a volume integral over the volume V, again V is contained within the surface area A, and all you have to do really is to make the integrand of the volume integral the divergence gradient dot psi. Okay, this, as you probably recall, is the so-called divergence theorem in your math class. Why do we use this divergence theorem? Because Gauss's law. Okay, let's take a look at, for example, Gauss's law for electricity. It starts with a surface integral, right? So what I'm going to do is I'm going to convert this surface integral into a volume integral. Okay, for the left-hand side. Now the right-hand side is originally it is equal to Q enclosed over epsilon naught, right? What I'm going to do is I'm going to rewrite this Q also as a volume integral over the same exact region V. Then I can compare the two integrands on both sides. Okay, see how we do that. First of all, the left-hand side, what is that equal to? This is equal to, according to the divergence theorem, okay, the surface integral E dot dA equals the volume integral V of gradient dot E, or the divergence of E dV, right? And the other side, 1 over epsilon naught times Q, that is the charge enclosed. If the charge density inside is rho, then all you really do is integrate rho over dV. Eh? You see that? Okay. Now, this tells us that gradient dot E integrated over this volume equals rho over epsilon naught integrated over the same volume, right? Now, normally, when two integrals are equal, they're equal to each other over the same range, there is no guarantee that the two integrands must be the same. For example, sine and cosine, if I integrate both of them from 0 to half a pi, you know the answer is the same, right? The answer is the same. They're both equal to 1. On the other hand, doesn't mean sine and cosine equal to each other, right? But our situation is a little different. Our situation is a little different. As a matter of fact, you notice that this V is not a fixed volume. Rather, it can assume any shape and size. Okay, V is an arbitrary volume, just like the area A is an arbitrary area, and therefore, this tells us that these two integrals are always equal to each other, no matter what region of integration you choose. Okay, now that means that the two integrands must be the same. Okay, you know, with sine and cosine, the integrals are not equal to each other if you go from 0 to, for example, a quarter of a pi. You know, you don't get the same value, right? But with this case, no, regardless of what V is, these two sides are always equal to each other, and that tells us that the two integrands must be the same, and therefore we say gradient dot E equals what? Rho over epsilon naught. Okay, this is known as the differential form of Gauss's law. And that one, of course, as we learned before, is the integral form because it contains the integral. This is the differential form. Now, we have never used the differential form before. It's because in our case, we only study special cases where it's either high symmetry or ideal conductors. So this integral, we made sure the problems that we try to solve, the integrals are so simple that I can simplify this integration, such as making E and dA equal to each in the same direction, and then E has the same magnitude over the area A, so I can take it out, that sort of thing. But in general, you may not have that kind of symmetry. So in general, you may have to solve either this integral equation or this differential equation. And given a choice, most of us would probably favor a differential equation over an integral equation. Okay, so you know, in more advanced courses, the differential form is actually used more often than the integral form, which is only easy under special circumstances such as symmetry. Okay, so that's how we convert the first equation into the Gauss's law for electricity into differential form. Similarly, what about Gauss's law for magnetism? What is that equal to? Well, the other side of the Gauss's law of magnetism was equal to 0. Okay, that is because there is no such thing as magnetic monopole, so you don't have rho. This rho is for the electric charge here. You don't have a magnetic monopole, so therefore, this is simply equal to 0. This is the differential form of Gauss's law for magnetism. Okay, now mathematically, it means that there is a longitudinal component of the electric field which is picked up by this differential operation gradient dot, or the divergence. Okay, what is that equal to? It equals the charge density divided by a constant epsilon naught. And the second equation tells us that the magnetic field cannot have any longitudinal component. In other words, it's a purely transverse field. Okay, because there is no magnetic monopole. Okay, so these two equations take care of the longitudinal components of the E field and B field. So, how many more equations do we need? Well, since each field, E or B, would in general have a longitudinal and a transverse component, I'm going to have to use two equations, right? One describing the transverse component, the other describing the longitudinal component for the same vector field. And so therefore, E and B each would need two equations. So 2 times 2, what do we get? We get a total of 4 equations. Isn't that the number that we already have? Okay, so we have the right number of equations given by these 4 laws, and then we are going to continue to convert each of them into differential form, and let's put them all together on the same page. Let's see what happens if we do that. Okay, now these are the 2 longitudinal components. Now let's look at the transverse component. Alright, for the transverse component, we have to use another mathematical theorem, and that is called the Stokes theorem. Now I'm sure you've heard that before, you've studied that before in your math class. Okay, so what does it say, if you recall? Well, it says that if I have a loop integral or contour integral C, okay, over a contour C for this vector psi dot ds contour integral, I can convert it into an area integral A over area A. A is enclosed by the contour C. Okay, all you have to do is to use the rotation or gradient cross psi, the rotation of the vector field psi, integrated over the area A, which is enclosed by the contour C. Now, this tells us that we can convert Ampere's law into differential form. Let's see how we can do that. Okay, first of all, the left-hand side right now is a loop integral. I'm going to convert that into a surface integral using Stokes theorem. Okay, so this side is equal to what? Integral over area A, gradient cross B dot dA, right? Now the right-hand side, mu naught I is the total current going through the surface. I can write it as an integral, surface integral of the current density J, okay? J dot dA. Right? That's by definition of current density. And once again, since these two integrals are always equal to each other over the same area A, regardless of the shape and size of the area A. Okay, to make that happen for all possible areas A, we must equate the integrands of the left-hand side and the right-hand side, and therefore we say gradient cross B, which is the integrand of the left-hand side, must equal to mu naught times J, which is the integrand of the right-hand side. This is a differential form of Ampere's law. Okay, so as you can see clearly, to get the transverse part, to describe the transverse part of a field, we have to use the rotation operation, gradient cross instead of gradient dot. So the last one to be converted is the integral form of Faraday's law, which says that epsilon equals negative d phi by dt, which is to say that the loop integral, the contour integral E dot ds equals negative ddt of our surface integral B dot dA. Here A is enclosed by the contour C. Now we use the same idea as we have here, and that is I'm going to convert both sides as to an integral over the same range. Right now the right hand side is over the area A, the left hand side is over contour C, which encloses the area A, so I'm going to convert that contour integral into an integral over the same exact area A using what? The Stokes theorem again. So this can be written as gradient cross E dot dA. Okay? Now, how do I extract the integrands out? Left hand side is gradient cross E. Okay, gradient cross E. And the right hand side equals what? Negative sign. Move that ddt into the integration. So you are taking the time derivative of b. Okay, now b depends not only on time but also on space, location, and I'm only taking derivative with respect to time, and therefore I just use the partial derivative sign. That is integrand on the right hand side. So that is the differential form of Faraday's law. Okay, so this one describes the transverse part of the magnetic field, and this one describes the transverse part of the electric field. Okay, so now we can finally put everything together. We have all the four laws in both differential and integral form. Okay, let us see what we come up with. Gauss's law for electric field, Gauss's law for magnetic field, Faraday's law of induction, and Ampere's law. Okay, you can see why there are four such laws for E and B field. No more, no less, because again, it takes a longitudinal and a transverse equation for each field, and see there are two fields, total of four. Okay, converted to differential form, gradient dot E, that describes the longitudinal part of the electric field. Here's the longitudinal part of magnetic field, which doesn't exist, and here's the transverse part of the electric field, and here's the longitudinal part, transverse part of the magnetic field. Okay, so this equation set is called Maxwell's equation. It is attributed to James Clerk Maxwell, who was widely regarded as the most important theoretical physicist of the 19th century. Okay, so it's the same Maxwell, by the way, that gave us the Maxwell-Boltzmann distribution in physics 1b. Remember that? Okay, it's the same Maxwell. Okay, so this is the culmination of the classical theory of electricity and magnetism. Everything that we need to know about electromagnetic phenomena is hidden in these equations. So in theory, all we have to do is solve these equations, and we can get whatever we need to know about any electromagnetic phenomena. Okay, but you say, wait a minute, why do we call them Maxwell's equations? Aren't they discovered by different physicists? Well, this is Gauss's law, Faraday's law, Ampere's law. So what did Maxwell do to deserve this credit? Did he simply put everything on the same piece of paper? Is that all he did? Well, first of all, putting everything on the same piece of paper in his era, okay, we're talking about the 19th century. That was not easy, okay? This was far from the internet era. People did not communicate easily with each other. And to put different laws discovered by different people at different time and different location together to form a complete picture, that in itself is a big achievement. Okay, this is for the first time people can see the entire picture of E and M. But that is not all Maxwell did. It turns out that when Maxwell took a close look at these equations, he found that one of these four equations was not entirely correct. Okay, it turns out that he had to modify one of these three laws. Actually, one of these four laws. He had to add a new term, and that new term plays a crucial role to one of the most important phenomena of nature, and that is the so-called electromagnetic waves. Without electromagnetic waves, no energy from the sun can reach us. The planet will not be able to survive. We will not be able to survive. Okay, and there wouldn't be such thing called light. So, what is that mysterious term that he discovered, and how did he do that? Well, we can actually get a clue from the symmetry of the electric field and magnetic field. And let's see what we have. You see, if I look at the differential form of Maxwell's equations, okay, differential form Maxwell's equations. I'm going to box them. I'm going to single them out. These are differential equations. Four differential equations. This one says that the longitudinal component of the electric field is given by the electric charge. Okay? And this one says the transverse part of the electric field is given by what? A variable or time varying magnetic field.